So today we're going to talk about multicolinearity, and the question is, what is multicolinearity? X variables are highly correlated. That's sort of exactly it. So what is wrong with, so X are the covariates or the features, right? So we regress Y on, let's say 1 plus beta 1 x1. So this is usually x0 plus beta 2 x2 all the way to beta p xp. So the x's are correlated. So correlated, what does it mean? So if you think of the x's as random variables, then covariance, correlation, these things make sense. Here you're thinking of x as fixed. So you can think of them as basically samples from a distribution. What we're looking at is an empirical notion of correlation. And rather, you can think of it as correlation, inner product, stuff like this are similar. So x1, x2, and xp, let's say some of them are correlated, is related to the idea that they span the same space, or one can be explained by linear combination of the other ones. So that's why it's called multicollinear. For example, I can write x2 as a linear combination of x1 and x3, for example. Then it means that x2, for example, x2 could be in the span of x1 and x3. So then it's multicollinear with them because it's in the same subspace spanned by x2 and x3. Okay. This can't happen under the assumption that we have. So what is the assumption in the design matrix that you started with? Yes.
Full rank.
Full rank. So you have like n rows and then p, let's say plus 1 columns, and p plus 1 is less than. So you have full column rank. So this would violate that, because this would mean that the rank can't be, so one of them is redundant at least. The rank is at most like p. So under the full rank assumption, this can't happen. Under the full column rank assumption. However, sort of an approximate version can happen. So this might not be exactly true, but approximately true. So approximately means, let's say, for example, if I project x2 onto the span of x1 and x3, if it's in the span, it would be exactly itself. If it's not, there might be some residual, but it might be close. So when I project this onto the span of x1 and x2, I get a good explanation. So it could be approximately true, i.e. residual of the projection, residual, say, resulting from the projection of x2 onto the span of x1 and x3 could be small. Okay. So from a statistical perspective, what does it mean to project onto the span of regress? Okay, exactly. So if you're a statistician, thinking of projection, thinking of regression is sort of the same. So the statement that I'm saying here, like writing here, is back up a little bit here. So the statement that I mentioned there, so this is sort of equivalent, equivalently. If we regress x2 onto x1 and x3. So you treat x2 as the response variable, x1 and x3 as the covariates. I regress it, then we get a good regression. Then we get a good model. Or like good fit. Good model fit. Which can be measured in many different ways. So how can I measure the fit of a linear model? R squared, yeah, so that's the perfect measure. So R squared, for example, in which case I will say R squared 2, for example, in this model. Not 2, okay, R squared. That's a slightly different regression, but there is an R squared attached to this regression, and it measures how well it fits. If R squared is 1, what does it mean? No residual, so we're back in that setting. So x2 is actually explained completely by x1 and x3. Under our assumption, hopefully that doesn't happen, but R squared could be very large. Okay, and if you remember, R squared is sort of some sort of a multivariate notion of correlation. So that exactly captures what we care about. So you see, like there is some sort of a measure of how, like we can sort of measure multicolinearity, and you don't have to restrict yourself to x1 and x3. What will happen is we'll see that the good measure is try to regress x2, for example, on everything else. So pick x2, and then all the other variables go into the regression. So you regress x2 onto all the other variables. That gives you some R squared. If that R squared is high, it means that x2 can be explained by the other variables. And so you have the multilinearity situation. If that regression is small, like this R squared is small, then x2 is not going to cause a problem that much from a multicollinearity perspective, because it can't be very well explained by the other ones. It's like an independent variable, really. Right? So the idea of, like, if you want to generalize, is that you look at each covariate and regress it on all the other covariates. And look at, for example, the R squared or other measures of fit of that regression model. If it's a very good fit, then we have a problem. So we'll see what the problem is. But if not, then we don't have the multicollinearity situation arising from that particular covariate. Does that make sense? Yes.
This project like, so we project like x1 on like the span of like x2 and x3. But what like it would be like what about like x2 and x4? Or does it have to be like every permutation or every combination?
So can you say that again? So we project x1. So let's say I have 3 variables, right? So let's say we have p is 3. We really have 4 covariates. So the columns of R1 usually plus. So what do we do?
It's like one like so somehow we accept like x2 is like within the span of like x1 and x3. Will we have like project on the span of like x1, x3, but why not just like the span of x1 and why not just the span of x3? Why do we have the span of x1 and x3?
Good question. First, in this model, it's good to just project it onto a span of x0, x1, and x3, all the other ones. So that was, yes. But why not just a single one? So I can also project x2 onto the span of x3. Or I could do like onto a span of x1 and x3, or I could do onto a span of x not x1 and x3. Everything else, or a subset of everything else, you could do all of that. Right? But why do I want to project x2 onto the span of everything else? We'll see where that comes from, but anyone can like justify why just not project onto this or project onto this? Assess the goodness. It's a fit of the resulting model. So you can do what you propose. It's fine, but if you project x2 onto, let's say, x3, and there is like the R squared is small, what do you conclude? No, you conclude something that x2 cannot be explained very well by x3, okay? But it could be explained very well by x1, and that would cause the issue that we'll see, okay? Projecting onto a subset is okay, but just the information it gives you is that whether that collection of variables onto which we project can explain linearly this covariance. If it's not, so if it can, like, if it does explain very well, then you have an issue. So if I project x2 onto x3 and the R square is very high, already we'll have a multicollinearity issue. But if it's low, I still could have multicollinearity issue. So it's like a sufficient, so if it's like a good fit, it's a sufficient condition for concluding that you have multicollinearity. But if it is not high, there's still a possibility that other variables can chip in and explain. So the ultimate thing is to just predict onto everything else. If that's small, then none of the other variables collectively can come in and construct x2. Then we'll have no problem. Okay, is that good? That's a good question. Any other questions? So what is the issue with multicollinearity? Why would I? Anyone knows why it's an issue? No one has seen. So in this severe case where something like this happens, where the assumption of full rank is violated, the issue is that betas are not at all defined anymore. Okay, so what do I mean by that? Suppose I have just two variables, x1 and x2. Suppose we have two covariates, no intercept. No intercept. So I have y is equal to beta 1 x1 plus beta 2 x2 plus epsilon, let's say, okay? And suppose x2 is 3 x1, okay? One can be explained in terms of the other linearly. I can plug in x2 in there, right? So I get y is equal to, this is equivalent to saying under these two, y is equivalent, like this model is equivalent to beta 1 plus 3 beta 2 x1 plus 0 x2 plus epsilon. Right, so you plug in the value of x2 there, so you get that, right? So plug in x2, you get beta 1 x1 plus 3 beta 2 x1, which I'm collectively writing as this term, plus 0 times x2. So x2 is no longer in the model, but I'm just putting it there so that you can see. So I have basically redefined beta to be this and 0, and this is still a valid model. So when I try to go to estimate beta, there's no unique beta. Both beta work for the model. There's a situation where statisticians call the model Anyone knows what they call it in this case? But the parameters are, or the model is model slash parameters are not identifiable or unidentifiable. What it means is that I have two sets of parameters at least that give me the same distribution for y, exactly the same distribution. So from observing y, or the distribution of y, I can't recover the parameter. There's no way. Even if I give you the, like if there was no noise even, suppose there was no noise, I can't recover beta. There is no unique beta to be recovered. And this is not the only beta. Can anyone give me another sort of beta? So these two are, in the presence of this, these two models are the same. Can we have another one? So you can shift any amount of x2 onto x1 and vice versa and change the betas. So for example, if I want to write it as, let's say, whatever beta I want. So let's say I want to do like 2 beta 1 x1 plus, how can I do this? Can I do this? So you can do a lot of different things. It might be a little bit tricky to do it, but let me give you another example. Like I let's say keep one of, so this is x2 is 3x1, right? I keep 2 of it there. So let's say this is like 3x1, right? So I keep 2x1 here, put 1x1 there. So I get beta 1 plus beta 2 x1 plus 2 beta 2 x2 plus epsilon, right? Sorry, no, plus beta 2 x2. So if you plug in, okay, not that, something like this. So if I have beta 2 times 3x1 and then negative, is that correct? Or maybe this, 2 beta 1 x1. No, beta 2. No. Can you tell me how to like write another one? What I want to do. Beta 2 x2. So this would be like, okay, so let's try to do it. Beta 1 x1 plus beta 2 x1 plus 2 x1, let's say, plus epsilon. So I'll write it as beta 1 plus beta 2 x1 plus 2 beta 2 x1, let's say. And then I want to replace x1 with x2 over 3. Okay, so it would be like something like this, beta 1 plus beta 2 x1 plus 2/3 beta 2 x2. So that would be it. So if I haven't done it, so this is another one. Okay, so write it like that, take one here and then replace this with x2 over 3, so you get 2/3. So you can manipulate, you can basically get any kind of beta 1, beta 2 you want. So this is a serious issue. So there is no unique beta. So there's nothing to test basically. It doesn't make sense to actually test beta because there's no unique beta. So that's why we assumed the x's to be linearly independent or the x being full rank. Do people also understand the issue? There is something seriously wrong with the model. Not wrong, but so they can explain why, but there's no. So in this case, the projection is going to be unique. If you remember, I mentioned this in one of the lectures. Projection is unique. So if you try to fit this regression model, first you can't invert x transpose x, but you can solve the normal equations. give you some data. X beta hat would be fine. So all these models will give you the same X beta hat, but the data itself is not unique. So depending on the algorithm that you use, you could get a different beta hat. And even if there's no noise, you'd have problems. Sounds good? So this is the severity of the issue when there's this exact thing. But if there's no exact relation, it's still full rank, I get a unique beta, true beta, and then I get a beta hat. What will happen in that case is the variance of the estimates that we get for the betas for which we have multicolinearity issue is going to be very large. So there is a price that you pay in terms of the variance of the estimate that is due to the multicolinearity. So that's the issue that people worry a little bit about. It's like everything would be, I mean, not everything would be okay, but if the things are not severe, so the inference is going to be correct. But it's just that the variance for that data would be very large. So that's what I want to get at. Any questions so far? So before we get there, I want to maybe show, and then the other thing is we may be able to reduce like the model size, or we might drop some of the covariates. So the ones that are explained by the other one, we can drop without significant like impact on the performance of the model. So that's what you usually want to do. You want to drop the variables for which you have the multicolinearity issue. Okay, so let's see one example before I'll tell you exactly how it inflates the variance. So in practice, this is another manifestation. So you do the test. So for example, I have a regression model where Y is the sales in thousands of dollars, X1 is the number of ads, X2 is the cost of the ads. So it's like a pizza joint, and they spend money on advertisement and want to see what is the effect of the advertisements on sales. It's a very like classical business problem. They have two variables, the number of ads that they put out and the cost of the ads. And you can imagine that the cost of the ads is like correlated very much with the number of the ads. Let's say if all the ads were like priced exactly the same, then there's like a very like natural linear relation. So if every ad costs $2, like you had like the number of ads times 2 would be the cost of the ads. But the ad would vary in cost, so it's not exactly the same, but there's still a highly collinear relation. So what happens is when I do the regression, so this is small and it's hard to see. But what I want to do now is do it on my computer and also answer the question that was on the campus wire. So let's do this regression. So how do we do this regression? We do it here. So not sure if it's visible, probably not that visible, but can you see the screen? So the data is the pizza. So you could read it like this. Column names are, we can expand it a little bit. Let's see if I can. Larger. So okay, so column names are month, X1, X2, and sales. You can see the data. So for different months you get, so one of them is the sales, one of them is the cost. I guess this is the number of advertisements. The other x2 is this the number of like the price, and sales is thousands of dollars. Okay, so I want to predict sales based on x1 and x2. So what I'm doing here is doing the regression LM sales on x1 plus x2, data frame or like data using the data, and then the summary. Okay, so when you do the summary, so it tells you that you're doing this, residuals, some information about the residuals and the coefficients. So there's an intercept, and you write it like that. There's an intercept implicit. So the estimate is 24. The estimate of the intercept of x1 is 0.66. The intercept for x2, this is like beta hat 0. Beta hat 0, beta hat 1, beta hat 2. Okay. Standard errors you can calculate for different, like these are standard errors of beta hat. And then you have the t-values. These are the values of t statistic and the p-values. Okay. So the question was on CampusWire, what are these tests? So what is the t-value or the p-value is for what kind of test, or what are we testing when we produce or output these p-values? What is the, for example, test for which I have this p-value? So yeah, significance of coefficients, but what is the null hypothesis, let's say?
Beta, like each beta is 0.
Each beta is 0. So let's say then this p-value 0.024. What is the null hypothesis here?
Beta 1 is 0.
Beta 1 is 0. Okay. How about this?
Beta 2 is 0.
Beta 2 is 0. Yeah. So they're different hypotheses. So for each one of the null hypotheses, you have a statistic and a p-value. So they're testing different hypotheses. They're testing marginal significance of beta. So when I'm looking at this, I'm testing whether beta 1 is 0. I don't care about any other any other. And then when I'm doing this, I'm testing whether beta 2 is 0. And you're right that if you want to have simultaneous tests, then you have multiple comparison issues. We discussed this. Okay, so if you want to test whether beta 1 and beta 2 are both 0, you can take this into account, but if you want to have correct size, you have to adjust, right? Or you could do a more sophisticated F test. So you can, if, for example, if you want to reject the null hypothesis of either the sub, let's say, hypotheses are rejected, then you usually adjust your significance level by half, right? So if I want to test at level 0.05, the simultaneous hypotheses, I'm not going to reject at level 0.05, I'm going to reject at level 0.025. So if either of them is below 0.025, then I would reject. Then I have guarantees that I would, if I do the experiment many times, my size, the test would have 0.05. So you should understand. Go back to the discussion at the first lecture that we discussed general linear hypothesis. That's how you can use t-tests to do simultaneous hypothesis testing. But people use this as a more informal way. Just they look at it and see which coefficients are significant. The issue is that together there's going to be some issues. And this is an example where it shows the issues. So what this is saying is when I test whether x1 is significant, right? What I conclude here? It's not significant, and you can also see the stars. So stars here is usually how significant it is. There's nothing here. So it's the standard is 0.05, right? So it's above 0.05, so it's not significant. X2 is also not significant. Basically, individually when I test, neither is significant, right? But let's go down a little bit. So there's more information here. So residual standard error, what is this 2.7? What do you guys think this is? residual standard error in our notation. On 13 degrees of freedom. So where is the 13 degrees of freedom come? So this, how many samples we have? 16, right? How many covariates do we have? P plus 1, let's say 3. So 16 minus 3 is 13. Okay, so 13 is like n minus p minus 1. So what is this? It's just S, right? It's when you want to have an estimate. So we need the S goes into everything, right? S squared. So this is residual standard error, basically like norm of E squared divided by n minus p minus 1 and then the square root. Okay, because it's like a quadratic form, it has a certain number of degrees of freedom, which is this. We can verify that this is just calculate your estimate of S, and it should be this. Degrees of freedom, multiple R squared, just what we call R squared. It's called multiple R squared, so that's 0.77. It's just pretty high. So it's model is a good fit. Adjusted R squared, I'm going to discuss later. This is a slightly better version, which is good for model selection. And the F statistic. So now you have 22.9 and 2 and 13 degrees of freedom, p-value 5 point, let's say 5 to the 10 to the negative 5. So this is really small. So what is this F test? Like, what is this? Reporting? Your guess? Yes, okay. Like this is like when we talked about like significance of linear relations. So this is assuming the goal is like assuming that these covariates except the intercept. So beta 1 is equal to beta 2 is equal to 0. So it's testing that and using an F test, we can see that the two constraints, beta 1 is equal to 0, beta 2 is equal to 0. That's a Q2. And then 13 is the same as this, right? So this statistic is like the F statistic for that particular test that we have seen, significance of linear relation, or what we call ANOVA. It's one of the first ANOVA that we discussed. So that gives you that, and this and the p-value. So it gives you that's all the information here, except the adjusted R squared you should now understand. Okay, just you can also drive yourself exactly. Like all the things that come out of this, you should understand that. But there's a trouble here. So this is a very good model. First, you can see from the R squared, and you can also see the p-value here. Okay, so you reject the test that both coefficients are, the null hypothesis that both coefficients are 0, we reject. But when you did the test, the t-test is, we kept both. Sorry, so we did not reject the null. When I test whether beta 1 is 0, I conclude that it's 0. I don't reject. When I test whether beta 2 is 0, I conclude that it's 0. I don't reject. But when I test whether both are 0, I reject. So both can't be 0. So how do we resolve this issue? Do you see the issue? So if I do individual t-tests, I'm not going to keep any one. So when I test for x1, I decide that beta 1 should be 0. When I test for x2, I decide that the coefficient of that should be 0. But when I assume that both are 0, then this is saying, no, you shouldn't assume both are 0. If I assume both are 0, then this is this null hypothesis and this is rejected. So how do you explain this apparent contradiction? This goes back to the idea that these are testing different hypotheses, right? So if you think a little bit about that. It is pretty tricky, okay? But what happens, let's say, when I try to test whether beta 1 is 0? What will be the reduced model or the null model in this case? Yes, you have beta 0, 1 plus beta 2 x2. So that's our reduced model. And this model is not rejected. So what this test is saying is that if I keep x2 in the model, I can set the coefficient x1 equal to 0. This one is saying if I the opposite. If I keep x1 in the model, I can set the coefficient of x2 equal to 0. So if I have one in the model, I don't need the other one. So these tests are saying that. But this is saying, but you can't drop both at the same time. So things are consistent. So if you understand what you're doing here, there is the other covariate in the model. Because there is the other covariate in the model, I don't need this. When I test for this, whether it's 0, the other one is in the model, so I don't need this. But when I say I'm trying to drop both, this is saying you shouldn't drop both. So this is exactly the situation when you have multicolinearity. So one is enough to explain. In the presence of one, you don't need the other. So that's what happens when you do the t-test. You'd see that none of them are significant individually. But when you do the f-test, there is a relation. So one of them, you at least need one of them. But it's not clear which one. So you can drop either one. That's the tricky part. Does that make sense to people? So if you understand this, there's a lot of like intuition that you understand, like you get about the linear model, about the test that we were discussing. So these are doing marginal testing, whereas this is doing sort of simultaneous testing. Okay. So based on the conclusion, we can drop one of the covariates, right? But we can't drop both. Now the question is of which one I want to drop. You can keep both, but it's not recommended. Let's say I want to now drop one. Which one do you think it's good to drop based on the information here? X1, why? High p-value, yeah. So this is slightly seems to be marginal even it's, so this is testing the reduced model over just one of the covariates in there. So when I test whether I can drop this, the p-value is higher than this. So it seems like X2 is more informative. Okay. Dropping X2 is possible in the presence of X1, but it's less, so the p-value being smaller is better. So if you think a little bit about this. And you can also see, for example, if I do later, if I do LM against X1, so if I do a regression against X1, you can see it's very highly like significant. And if I do it against X2, you can see it also should be highly significant, right? But the p-value is hopefully smaller. Yeah, it's like 6.6, sorry, 2.22 to the -5. This is 1 to the -5, right? So this model is more either this, or you can look at the R squared of the model, 0.72, and here you have 0.75. And because these models have just one covariate, it's reasonable to compare the R squared. Okay, if they were nested, that wouldn't be that would be a little bit problematic. But this model has R squared 0.75, slightly better than this one, which has 0.72. So if you want to keep one, you would go with X2. Right. So how much you spend on ads, and also like intuitively makes sense. So you imagine that the quality of the ad is reflected in the price. So quantity is quality is better than quantity. It's like how much you spend is more informative than how many ads you. So everything works out, and I also have an intuitive explanation. But everything here you should understand, right? So once I drop one, the model becomes significant. And this, as you can see, the p-value here for the f-test and the t-test are the same. So again, if you go back to one of the things that I said before, when you do a single t-test, it's equivalent to the equivalent f-test. In this case, the f statistics is actually going to be square of the t-value. So if you do, for example, 6.536 to the 2, you should get that 42.72. Okay, and then the p-values would be exactly the same. So in these regressions, and you can see here as well. So the p-value for this and the p-value for the f is the same because they're testing the same hypothesis. And the statistics are basically squares of each other. So you can do an f-test for a marginal testing of a single covariate in the presence of the others. You could do an f-test as well. Just it's like an overkill for doing just so. F-test is a generalization of t-test, basically. Okay, sounds good. So now if you go back to this, you can see also that so look at the standard errors here, right? 0.05, 0.06. These are the standard errors of the coefficient. So here you have, for example, a coefficient which is 0.06, standard error is 0.5, which is pretty high, and that's why you have a p-value which is large. So this is very uncertain. You have like 1.2, and the standard is 0.7. It's pretty high. When I drop them, so for example, let's say, okay, I'll redo this. That's that, and then I do the single mode. So here's I have those coefficients. When I drop x1, you can see now the coefficient is actually 2, and the standard error is 0.3. The standard error is much smaller than, and then that's what you get, why you get a high higher p-value. So the effect size actually went up because it's so here it's like distributed between x1 and x2. So like a little bit of it is explained by x1 and x2. Once you drop it, the effect size of x2 goes up because it's taking the slack from x1. But surprisingly, the standard error also goes down, which is the thing that we want to discuss. There is inflation of this standard error because of multicollinearity. So the standard error of these coefficients is higher than potentially the noise level in the model, in a sense. So that's what I want to get at. So the fact that the standard errors are higher are what would lead to the fact that you don't need them. You don't need both. But once you drop, although the effect size goes up, the standard error even goes further down, and the p-value gets very small. Okay, so there is some inflation of the variance. That's what multicollinearity is causing. So it's like it was 0.7 and the effect size was 1.2. Now the effect size is 2, but the standard error is even smaller, 0.3. And you get a large t-value, which is just this divided by, so this 2 divided by this is t-value, and then you get the t-value as well. Sounds good? So you now understand what the LM is doing, what is multicollinearity, what is this f-test doing, what is the t-test doing. Hopefully you learn about adjusted R-squared as well. Questions? I'm just going to mention about this. So now I want to mention what exactly happens to that standard error. So we went over this, and you can just verify that everything that we did here just matches the slide. So we can't drop both, but given one, we can drop the other one. You can like write down the R squared. Based on the R squared, you can decide that it's only X. The model with only X2 is better than the one with only X1. And you can see the one with both X1 and X2 has higher R squared than either one, and which is expected because it contains the two models. So whenever you have nested relation, R squared is going to be like ordered accordingly. So the R squared of this model is strictly less than or equal to this, and similarly for that, because the bigger model contains the covariates of the smaller ones. But a priori, we don't know which one is bigger. It's not possible to compare them. Depends on the problem. Okay, so there's no point in including that. But so now I want to talk about the variance inflation factor. What is actually problematic is the effect it has on the variance of the estimates. So consider the linear regression model, and one can show that the variance of beta hat can be written like this formula. Okay, I probably try to prove it for you. So you have this as well. So we know we have a formula for the variance of beta hat. Anyone remembers? We calculated the variance of beta hat actually. Yes.
The variance matrix of beta hat?
The variance of beta hat. So yeah, the covariance of beta. Okay, correct. So beta hat is a vector. The covariance matrix of beta hat. Here, I want to look at this. The jth.
Just the diagonal to that matrix.
Yeah. So jth element. So let's say if I have. So what was the covariance matrix?
And it was sigma squared times xtx1 in the inverse.
Yes.
You don't really know sigma squared, so we approximated it, and that's squared.
Yeah. So here I'm talking about variance. If I talk about variance hat, and then not this one, but yeah. So if you had variance hat, that's the estimate. I would put like s squared instead of sigma, and the rest is the same. Okay. So here we're talking about the actual variance. But if you want, you can put, if you like, you could do hat here, and then you change this to s squared. Everything else would be the same. But the point is, we already have a formula. You can calculate the jth entry of this, let's say, and it would be the jth entry of this. So you have to invert this matrix and calculate the jth entry. So you can see the sigma squared is there, but the rest is basically the jth entry. I've written it in this format. So what is this? N minus 1 times variance hat of xj. Variance hat of xj is the jth column. Variance hat is just the empirical variance of that column. So that's this notation. And so n minus 1 times that is basically just the sum. So that's there, and then times the factor. This is the factor which is called variance inflation factor. So 1 divided by 1 minus rj squared. What is rj squared? It's exactly the r squared of regressing the j covariate onto everything else. So when I regress xj onto the other ones, that's a regression problem, has an r squared. I'm calling it r squared j. So it's different for every covariate because it's a different regression problem. So this is r squared the regression xj onto the rest of the covariates. Right. So if r squared j is close to, if it's 0, then this is just 1, there's no inflation. If it is close to 1, this gets what? Close to 0, and then 1 over that goes to infinity. It's close to infinity. So you can get very large variances as this R squared J approaches 1. And the reason why you get large variances is not because of the noise level. The noise level of the problem is sigma squared. So this could be the same, but because you included the variance in the model that correlate with this one, it would inflate the variance of beta. Okay. So it's a factor completely determined by the X matrix, not the noise level of the problem. So there's a natural noise level in the way that we model the problem. Y is, so there's this epsilon, this has the noise, but this factor is not coming from it. So the noise here is just going to appear here. This completely determined by the multicolinearity. This factor here, variance hat of xj, it should be there because we have seen, like, if I rescale covariance, I rescale the beta, right? So if I scale down, so if I rescale the j term by a factor of 2, so divide by 2, right? So this is divided by 2. So if I divide everything by 2, this is, so whatever variance I had is divided by 2, goes here and then just flips to the numerator. So I multiplied the variance of beta hat by 2 because I multiplied beta hat by 2. If you remember, if I divide the j column by 2, the effect on beta hat is that I multiply beta hat by 2. So the variance is going to be multiplied by 2. So this is accounting for that, just the scaling. So if you normalize the columns to have unit variance, this is going to go down, like go away. So this is going to be 1 for standardized design if you normalize the columns of X to have unit empirical variance. And then let's say I do that, so this goes away. So this is there to account for rescaling. If I rescale, there's a natural, this is like mathematical property. It's not a statistical. So this, I rescale the covariance. Now I fix this to 1. Then this has a lot of meaning. So this variance goes down like sigma squared divided by roughly n. Forget about the n minus 1. It's like sigma squared divided by n. So that's how the variance goes down. If you have more samples, you have a more accurate estimate. So the way that it goes down is like variance of beta hat j would be roughly sigma squared over n times 1 over 1 minus r squared j. So this part is the natural scaling of parametric estimates. So the variances of your estimate, this is like unbiased, and the variance goes down like 1 over n. So the more samples you have, the smaller this is. And the estimate of your variance, the standard error is also going to go down. Okay, so more samples is better. This part is tricky. It's the factor that's causing the inflation unnaturally if you have multicollinearity. Okay, it's a very nice way of writing. This is like linear algebraic. It's not very intuitive, and you can also see why I usually divide by n. If you've seen the homework problem, I usually write it like this divided by n and this divided by n, because this is some sort of the correlation. So this, if you rescale the coefficients, this thing is going to be stable, and then you get the sigma squared over n here, which is going down. That's maybe another time. Okay, that's that. So I just want to maybe mention how this is derived. And there is another alternative way of arriving at variance inflation factor. So how this is derived. Any questions? I just want to quickly prove this. So how do you prove this? Anyone knows how to prove it? The idea is like a linear algebra trick, how to get access to the jth element of the inverse of a matrix. Okay, so what I have is like I have X. I'm going to write it as xj. Xj is the jth column. I'm going to put it in the first column for simplicity, and x minus j. This is something that people often do. Although it's the jth column, is really the jth column. So this is xj. The rest is I'm calling x minus j. But once you get comfortable with linear algebra, you'd see that I can permute the column so the j column is the first column. And I can do everything as if the j column is the first column and then permute back. If this is problematic for you, think of just the first column. We're doing the first column. Okay. But I'm writing it as the first column. The rest, this is like 1 by, let's say, p, this is n, so n by p plus 1. So then x transpose x, you get xj transpose. X minus j, this is the rest. This is a matrix transpose times xj, capital X minus j transpose. No, not transpose. There's no transpose. And if you multiply out, you get xj transpose xj, this times that, and then you get this times this. So xj transpose capital xj, x minus j transpose xj, and then you get x minus j transpose x minus j. Okay, x minus j is just my notation for all the columns except j. Okay, it's not something. I should probably not put this because this is like very confusing. I'm just going to put minus. So xj is the jth column. Okay, to avoid too many. Yeah, so let's do this. X minus j. This is going to be xj transpose x minus j, x transpose minus j times xj, and x, yeah. So that's that. So this is 1 by 1, 1 by p. This is p by 1, and this transpose of this other term, and this is p by p. Okay, so I want to now invert this. What I want to do is do the inversion. So the inverse of this, which is the inverse of that, I want to invert this and write down the first element of the inverse. And the trick here is if you have a block diagonal matrix, A, B, C, D, when you try to invert it, there's a trick, or actually there's something called the Shor complement that comes into play. Anyone knows the Shor complement? What is the Shor complement? Yeah, we don't have much time, so otherwise you could do Google Shor complement. I think probably write it. Shor, something like that. Complement. Shor. So if I have basically the process of Gaussian elimination, you can do it in a block format. You can make this block 0 and then that block 0, and then you can read off the inverse. So if this matrix is M, in Wikipedia notation M/D, if I'm not wrong, this would be the Shor complement, one of the Shor complements. So there will be A minus B, B minus 1C. Okay, so it goes like, this is a very useful property. So A minus B, B inverse C. If D is invertible, you get that, and the first block here would be MD inverse. Okay, so if D is invertible, we can form this Shor complement, and that will be the first block. The rest you can also write. It's not of concern at this moment for us, but the main point is that the inverse of that Shor complement gives you the inverse of the first block. In our case, the first block is 1 by 1, so that's also going to be 1 by 1. But if you write this down, this is going to be our A, right? So this is write it as. So this is going to be A. This is going to be. I'm going to write it as B transpose. I'm going to write this as B, And I'm going to write this as, yeah, okay, yeah. It's okay. I can do B, C, and D. Okay, it's maybe easier. So what we get here is going to be, A would be, in our case, would be xj transpose minus B would be xj transpose x minus j. D inverse would be x minus j transpose x minus j inverse. And then you get C, which is x minus j transpose xj. Okay, so that will be this. And this I can write in a more natural way. So it's going to be xj transpose here and xj here. This would be I, because when I multiply both sides, I get the first term minus, I'm basically factoring out these pieces. And this middle guy is going to be just this guy. X minus j transpose, x minus j inverse, x minus j transpose. So if you multiply out, this times I gets you the first, and the second, I'm just basically factoring out these pieces. These are common from both sides. So now, do you recognize what this is? So yeah, so we can call this H minus J. It's the hat matrix for regressing onto those columns. So this is I minus H. So what you get is like X transpose I minus H minus J xj. Or if you can write it as, because I can put a square here. So this is the same as I minus H J, sorry, minus J xj squared. So if you square this is like a quadratic form because this is idempotent. So you get X transpose I minus Hj squared xj, which is the same. So what is this quantity? This quantity. I minus H times xj here plays the role of y. So this is the residual vector in regressing xj onto the rest of the columns. Okay, that's the formula for the residual. So this is really SSE j if you want. It's the SSE in the regressing of xj onto the rest of the columns. Okay, so what we have shown is that the first element here is just going to be SSEJ inverse. Okay, because that's the short complement. This is going to be the inverse of the short complement. Right. So when I do this, I have like sigma squared here. There's sigma squared there. I have a sigma squared here, and then this SSEJ inverse. Okay. So really at the end of the day, this quantity that I want is going to be sigma squared divided by inverse of it. It's basically sigma squared divided by SSEJ. That's the real formula. Okay, it's a very nice formula. Sigma squared divided by SSE, like SSEJ inverse is just 1 over SSE because it's like 1 by 1. Okay, so this element is 1 by 1. So what I would get is sigma squared divided by SSEJ, and SSE, and then you can also verify that this really is SST in that regression. So if you multiply both sides, if you think of this is the jth column, right? This is basically how you calculate the SST is just you look at the y, you subtract the mean, square things, that would be the SST. So this is the SST in that regression when you regress xj onto, you can say this is SST j. Okay, so what I'm having here, I can write it as sigma squared divided by, I'm going to multiply by, so SSTJ and then SSEJ divided by SSTJ, right? So you get sigma squared SSTJ, and this quantity is just, what is this? It's the opposite, like 1 minus r squared j. Right, so that gives you the formula. So SSTJ is really this quantity that's there, and so you get that formula. Yes.
So, but this, if you don't know sigma squared, you can't actually find a value for that?
So this is the actual variance. If you,
There we
yes, but you can estimate it. The estimate would be just you replace sigma squared with s squared.
go. But we really, this part, we really care about the second half of that formula with the R squared.
Yes, yes, that would be the same. Yes, yes. So either this is the actual variance, your estimate would be just replacing this s squared. The rest you know, right? So you can write a standard error in the statistical composition as well. Okay, sounds good. Just a little think a little bit about this. This is really the SST in that relation. So really SST times this, what we get is like 1 over the SSEJ basically. Okay. But SSEJ, write it like that, makes it much more natural. Okay. So in the remaining time, I just want to mention there's an alternative way. So this is the nice way of looking at it. There's an alternative way which will not have enough time to go into details. But what you can do is you can form the sample covariance, the sample covariance of the columns. So what that is I'll let you read this for yourself, but in the end you get a sample correlation coefficient matrix, the sample correlation coefficient matrix, where each entry is the correlation coefficient, sample correlation coefficient between two of the covariates. And when you invert this matrix, the diagonal entries would be these variance inflation factors. So another way of writing VIF, so this is called VIF variance inflation factor, is 1 over 1 minus RJ squared, and it turns out to be also the jth element of the C inverse. This one you can also prove. Okay, it's not that difficult, but this is the one that's usually very useful. This is the one that's useful if you have the actual correlation matrix. If you invert it, the diagonal entries are going to be this. I like this interpretation better because it's much more obvious. But if I give you the correlation matrix, that's one of the exams, practice exams, gives you the correlation matrix. You can read off the variance inflation factors from the diagonal elements. In the case where you have just two covariates, you can write down the sample correlation coefficient. So we write that, and then VIF will be 1 minus. So when you invert it, you get something like that. And then the diagonal entries will be 1 minus the correlation coefficient squared, which is also the R squared. When you have two variables, the correlation coefficient R squared is the same. So in that case, everything reduced to the same thing, but this formula is also useful. Okay, so we're done with this. There's a set of slides that I also uploaded, which we won't have much time to go over. Hopefully, Jan went over it yesterday, influence and leverage. If I have time, I will come back. It's not something which is very difficult. So next time, I'm just gonna talk about model selection. That's the main remaining topic. And if you have time, I'm gonna go over this. Otherwise, if you missed yesterday's discussion by Ian, there are videos of this. So go through the past videos, lecture videos. If you have difficulty understanding this, I explain it. It's not something difficult. It's about detecting outliers, basically. So next time we're going to come back and talk about model selection. I'm hopefully going to upload those slides. Thank you, and see you next time.